Welcome to the lecture series of network theory. So, lecture number 2. So, in a previous lecture, we will discuss about series RLC circuit, and transient response. What is transient? How the transient will be in RLC circuits and all. So, what is transient? The XL equal to XC. So, at the transient condition, the circuit will be acting as a pure resistive circuit. So, at the time, the energy is transferred between inductor and capacitor. So source will not supply any power to the inductor and capacitor. So at that condition we can also call it as an exchange of energy between inductor and capacitor in the way of the inductor is transferring the electromagnetic energy is transferred to the capacitor, and the capacitor is transferring the electrostatic energy. So this is energy conversion. So magnetic energy is converted into electrostatics, as well as electrostatic energy is converted into magnetic energy. So these and all we are discussing in the previous lecture. So in this upcoming lecture, we are going to see about problems in series RLC circuit, and also we are going to discuss about parallel resonance. The problem: a series resonance network consisting of a resistor of 30 ohm, a capacitor of 2 microfarad, and an inductor of 20 millihenry is connected across a sinusoidal supply voltage which has a constant output of 9 volt at all frequency. We need to calculate the resonance frequency, current at the time of resonance, voltage across the inductor VL, and the capacitor at resonance, capacitance value C at the condition of resonance, the quality factor, and the bandwidth of the circuit. Also, sketch the corresponding current waveform for all frequencies. So, we draw the circuit, which is a series RLC circuit with the values given the sum. So, it is excited by the 9 volt supply with the constant frequency. Okay. So we need to find out the resonance frequency. We know that the equation for finding resonance frequency FR, that is equal to 1 divided by 2 pi root of LC. This is equation for an RLC series set. So FR equal to 1 divided by 2 pi root of LC. So we know the value of inductor and capacitor. So we can find out the resonance frequency at 796 hertz. Right. So next we need to find out the circuit current at resonance IM, that is maximum current at what is the maximum current in the circuit. So we know that so the resonance condition XL and XC both are get cancelled, then circuit will be purely acting as only resistance, it is having only resistance. So I equal to V by R as like Ohm's law. So from that we can find out the value of maximum current at 0.3 amps at the time of resonance. Next, we need to find out the inductive reactance at resonance. That means XL. So XL, that is equal to 2 pi F into L. So 2 pi the frequency. So we need to find out the resonance frequency. So for the F we can substitute the resonance frequency value 796 hertz. So XL equal 2 pi FL. So 2 pi FR resonance frequency into the inductor value. So inductive reactance XL equal to 100 ohm. So we need to find out the value of capacitive inductance, right? XC, that is 1 by 2 pi FC, we can also find out. Okay. So now some next we need to calculate the voltage across the inductor and capacitor, VL and VC. We know that at the time of inductor, at the time of resonance, the VL that is equal to VC. So what is the VL equal to VC? So in that we know the value of VL equal to I into XL. So value of I, that is equal to 300 milliampere or 0.3 ampere. The XL, the inductive reactance, that is 100 ohm. So from that we can find out the value of in voltage across the inductor in the same way. But in the same way we can also find out the voltage across the capacitor. But in a short way, we know that at the time of a resonance, the voltage across the inductor and voltage across the capacitor both will be same. So the VL, that is equal to VC. We need to calculate the VC. Note that is, the supply voltage may be only 9 volt, but the resonance, the reactive voltage across the capacitor VC inductor will be VR 30 volt peak. But okay, right? The what is this? We need to note down that the supply voltage is only 9 volt. Our supply voltage is only 9 volt, but in that across the inductor and capacitor, we are getting the value of 13 volt. How? Right. So quality factor, we know Q equal to XL by R. So XL equal to 100 and the resistance value is 3. So Q quality factor equal to 3.33. So from that we need to find out how to find out the bandwidth. So bandwidth, that is equal to resonance frequency divided by quality factor. So resonance frequency is 796 divided by the quality factor is 3.33. So bandwidth is through 238 hertz, right? So from that we have two values, the bandwidth, upper cutoff frequency and lower cutoff frequency we need to find out. So FL, lower cutoff frequency, that is equal to resonance frequency minus 1 by half of the bandwidth. So resonance frequency minus 1 by 2 the bandwidth, that is 796 is the resonance frequency, half of the 232 minus, subtracting we can get the lower cutoff frequency of 677 hertz. So for higher cutoff frequency, FR plus 1 by 2 bandwidth, that is equal to 796 plus 1 by 2, 232. We can get 915 hertz. So this is the lower cutoff frequency and this is the higher cutoff frequency. The resonance frequency is in between these two values, that is 796 is the resonance frequency. Okay. So we can draw the curve. We are representing the values here. I, that is a maximum current. So we can draw this frequency with respect to current. So this is a lower cutoff frequency 677. This is a resonance frequency 799. So at the resonance frequency, the maximum value of current is 300 milliampere. And at 915, this is the half of the value. From that, this frequency is 67, 677, and 915. At this frequency, you can get the value of 212 milliampere. This attained. So this is the current waveform. At the resonance frequency, we can get the maximum current in this circuit. Right? Okay. I think now I have some idea about how to solve the problems in series RLC circuit. So from that we solve. So you can take it as a one workout by your own. This is problem number 2. A series circuit consists of the resistance of 4 ohm, an inductance of 500 millihenry, and a variable capacitance connected across 100 volt. Clear? Variable capacitance connected across 100 volt 50 gauge supply. Calculate the capacitance required to produce a series resonance condition and the voltage generated across both the inductor and capacitor at the point of a resonance. So this is the question. So we need to find out this value. So here we have some, that is the time of XL equal to XC we know. So XL equal to 2 pi FC, or so XL equal to 2 pi FL. So we can find out the value of XL. So we know XL equal to XC. So from that we can find out the value of capacitance. Clear? So we know the value of inductor value. So at the resonance, definitely XL equal to XC. So from the data availability, so XL equal to 2 pi FL. So we need to find out the value of XL, that is equal to XC. But we don't know the value of XC. 1 by 2 pi F, we don't know the value of C. So from that, we can find out the value of capacitance. This is the method. you can find out the unknown capacitance value at resonance condition. Clear? Okay. So next we are going to discuss about parallel resonance. What is a parallel resonance? So before that, we know what is the resonance. So till now we discussed about the resonance in a series RLC circuit. Now the same definition, resonance, we are discussing in a parallel circuit. So how the parallel circuit will be performed at the time of resonance. You can see here. So resistance, inductors and capacitors both are connected in parallel across the voltage source. So here we know that the current is circulating. So because of the inductor will receive the capacitor. So capacitor will discharge and again inductor will. So we are providing this circuit will provide in this between the inductor and capacitor. This is providing the circulating current between these two conditions. Okay, let us define what we already know about the parallel resonance admittance. That is 1 by Z impedance. So reciprocal of impedance, that is called admittance. So 1 by Z, that is equal to root of G square plus B square. So what is G square? R square plus X square. Right. So conductance, that is equal to G is equal to 1 by R, reciprocal of the resistance, that is G square. Inductive susceptance, so XL, here we are mentioning it a BL. So in a series resonance, XL equal to 2 pi FL, but here we are reciprocaling, so 1 by 2 pi FL. In a series resonance circuit, X equal to 1 by 2 pi FC, but in this parallel resonance, capacitive susceptance. So there we are mentioning impedance. Here we are susceptance, reciprocal of the impedance, that is susceptance. So B is equal to 2 pi FC. So all the values are getting reversed, reciprocal. A parallel circuit contains the resistance R, an inductor L and capacitor C will produce the parallel resonance, also called anti-resonance circuit. That is opposite to resonance, that is called anti-resonance. When the resultant current through the parallel combination is in phase with the supply voltage. At resonance, there will be a large circulating current between the inductor and the capacitor due to the energy of oscillations. Clear? At resonance, there will be a large circulating current between inductor and capacitor. We will see in the first slide in the diagram. We are mentioning circulating current. It is providing a circulating current due to energy of oscillation. That is, energy is transferring between inductor and capacitor. Then parallel circuits produce the current resonance. So the parallel circuit will producing the current resonance. That is, current is circulating, but in a series the voltage is transferring. Here the current is, so parallel circuit produces the current resonance. So current will be this here, right? A parallel resonance circuit stores the circuit energy in a magnetic field of inductor and electrostatic field of the field in the capacitor. This energy is constantly being transferred back and forth between the inductor and capacitor, which result in zero current and the energy being drawn from the supply. So, as like we are discussing in the series resonance circuit, the energy is transferring between inductor and capacitor. The source will not supplying any power to the inductor and capacitor. The same way, in a parallel resonance, the current between inductor and capacitor both are getting transferred and interchanging. So the inductor and capacitor will not receive any, will not need any current from the source. Will not need any current from the source. That is here mentioning. This is because of corresponding inductance value of IL and IC will always be equal and opposites, and therefore the current drawn from the supply is the vector addition of these two currents and the current flowing in the resistance. So total current in the circuit is the vector addition of inductor current and capacitor current and the current flowing through the resistance. This is the total current flowing in the parallel resonance. In the solution of AC parallel resonance circuit, we know that the supply voltage is common for all the branches. So this can be taken as our reference vector. each parallel branch must be treated separately as with the series circuits, so that the total supply current taken by the parallel circuit is the vector addition of individual branch currents. Okay, each parallel branch must be treated separately as with series circuits, so that the total supply current taken by the parallel circuit is the vector addition of the individual branch currents, right? Then there are two methods available to us in the analyzing of parallel resonance circuit. We can calculate the current in each branch and then add together, or calculate the admittance of each branch to find the total current. We know from the previous series resonance tutorial, the resonance taken place when VL that is equal to minus VC, and this situation occurs when the two resonances are equal, XL equal to XC. That is the resonance condition. The admittance of the parallel circuit is given as Y, reciprocal of the impeller Y, that is equal to G plus BL plus BC. So it is we can write it as Y that is equal to admit 1 by R plus 1 by j omega L plus j omega C, or 1 by R plus 1 by 2 pi FL plus 1 by 2 pi FC. Resonance occurs when XL equal to XC and the imaginary part of Y becomes 0. Then XL equal to XC, we can call it as 2 pi FL, that is equal to 1 by 2 pi FC here. So we can rewrite this equation F squared, that is equal to 1 by 4 pi squared into LC. Also we can write F equal to root of 1 divided by 4 pi squared LC. So resonance frequency Fr, we can rewrite this Fr equal to 1 divided by 2 pi root of LC hertz, or omega r, that is equal to 1 by root of LC radius. So for a parallel resonance and series resonance, the resonance frequency is only depends upon 1 divided by 2 pi root of LC. To finding the resonance frequency in a series resonance or in a parallel resonance, the equations should be the both equations are same, that is resonance frequency equal to 1 divided by 2 pi root of inductor and capacitor values. Notice that at resonance, the parallel circuit produces the same equation as for the series resonance circuit. Therefore, it makes no difference if inductor or capacitor are connected in parallel or series. Also, at resonance, the parallel LC, that means inductor and capacitor tank circuits, acts like an open circuit with the circuit current being determined by the resistor R only. So the total impedance of the parallel resonance circuit at resonance becomes just the value of the resistance in the circuit at Z equal to R. Clear? So, so in this series, as like a series circuit, the same they are telling the frequency. Though if we are connecting the inductor and capacitor in a series or parallel combination, it will not affect the resonance frequency of the circuit. So both if the in a series resonance as well as in a parallel resonance, the equations to find the resonance frequency is same. So if you are connecting the inductor and capacitor in series or parallel, there will not be any changes in the circuit in the point of resonance. Also, the LNC, it will act as a tank circuit, so there is providing only circulating current. So the total current is only depends upon the resistance only the resistance that is available in the circuit. This is the diagram shows either side of the resonance, the current IL minus IC. This is inductor current and capacitor current is a maximum current. So both are getting circulated here. The xt equal to alpha. It will both are get cancelled. It will also at resonance. The reactive current is 0. So it will act as open circuit. So current flowing through this circuit is mainly depends upon the resistance R only, not depends upon inductor and capacitor at the resonance condition. Thus, at resonance, the impedance of the parallel circuit is at its maximum value and equal to the resonance of the circuit, creating a circuit conditions of high resistance and low current. Also, at resonance as the impedance of the circuit is now that of resistance only. The total circuit current I will be in phase with the supply voltage. So if the circuit is behaving as only resistance, so the current and voltage both are in phase. There is no phase displacement between the current and voltage because of the circuit is purely a resistive circuit. We can change the circuit's frequency response by changing the value of this resistance. Changing the value of resistance affects the amount of current that flows through the circuit at resonance. If both L and C remains constant, then impedance of the circuit at resonance Z equal to R maximum is called the dynamic impedance of the circuit. Clear? If both L and C remains constant, then the impedance of the circuit at resonance Z equal to R maximum is called the dynamic impedance of this circuit. Right? So impedance in parallel resonance circuit. So it is graph drawn between Z and frequency. So we know Z at the time of resonance, Z that is equal to R. So that is R parallel resonance is a resonance frequency. At the time of resonance frequency, it will get the maximum value of resistance, or is Z equal to R. The R is getting maximum. So we can assume that if the R value is maximum, automatically the current will be in so minimum. So here XC is greater, XL is very low. So here the capacity this will be because both are getting inversed. So XC is maximum. This in this part it will act as a inductive. In a parallel, XC is maximum. In this portion of the curve will be in a pure inductive circuit. If the capacitor value is high, the circuit will be act as an inductive circuit. But in the second half, if XL greater, XC is minimum. So at that time, in that time, the circuit will be behave as a capacitor. Because of in a parallel, we are interchanging these. So both are get interchanged. So if the XL is maximum, the circuit will behave as a capacitive circuit. If the XC is maximum, the circuit is behave as a capacitor. You can verify, you can compare this graph with the series resistance, you can find out the difference. Then this is the center point we can call as a dynamic impedance of this parallel resonance. Note that if the parallel circuit impedance is at its maximum at resonance, then consequently the circuit admittance must be at its minimum. Right? At one of these characteristics of a parallel resonance circuit is that admittance is very low, limiting the circuit current until the series resonance circuit. The resistor in a parallel resonance circuit has a damping effect on the circuit bandwidth, making the circuit less sensitive. Clear? Also, since the circuit current is constant for any value of impedance Z, the voltage across a parallel resonance circuit will have the same shape as the total impedance, and for a parallel circuit, the voltage waveform is generally taken from across the capacitor. We now know that at the resonance frequency Fr, the admittance of the capacitor is at its minimum and is equal to the conductance G given by 1 by R, because in a parallel resonance circuit, the imaginary part of admittance, example, the susceptance B is 0 because BL that is equal to BC, XL equal to XC likewise. So susceptance at resonance. So inductive susceptance, it is in a negative minus JBL. So it is in gradually increasing. Next susceptance, capacitive susceptance, it is linearly in linear. So next, total susceptance, we are adding these two. So in this point, we can get the resonance frequency, that is called resonance frequency. For the above, the inductive susceptance BL is inversely proportional to the frequency as represented by the hyperbolic curve. The capacitive susceptance BC is directly proportional to the frequency and is therefore represented by the straight line, linear. That's like the final curve shows the plot of total susceptance of the parallel resonance circuit versus the frequency, and is the difference between the two susceptance levels, inductor level and capacitance level. Then we can see that at the resonance frequency point where it crosses the horizontal axis, the total circuit susceptance is 0. Below the resonance frequency point, the inductive susceptance dominating, the circuit producing a lagging. You know that? That is, inductive susceptance is dominating, the circuit producing a lagging power factor, whereas the above the resonance frequency point, the capacitive susceptance dominates, producing the leading power factor. So, at the resonance frequency FR, the current drawn from the supply must be in phase with the applied voltage, as effectively there is only the resistance present in the parallel circuit. So, the power factor becomes 1 or unity. Also, as the impedance of a parallel circuit changes with the frequency, this makes the circuit impedance dynamic, with the current at resonance being in phase with the voltage, since the impedance of the circuit act as a resistance. Then we have seen that the impedance of the parallel circuit at resonance is equivalent to the value of the resistance, and this value must therefore represent the maximum dynamic impedance ZD of the circuit. So Z equal to L divided by R into C. As the total susceptance is 0 at resonance, the both are get cancelled and it will be 0. The admittance is at its minimum and is equal to the conductance G. Therefore, at resonance, the current flowing through the circuit must also be at its minimum, as inductive and capacitive branch currents are equal, IL equal to IC, and are 180-degree out of phase. We remember that the total current flowing in a parallel RLC circuit is equal to the vector sum of the individual branch current and for a given frequency. It's calculated IR equal to V by R, IL equal to V by XL, and XC equal to V by XC. So we need a total, we need to find out the total current IT equal to vector sum of IR plus IL plus IC, that is equal to root of IR square plus IL plus IC the whole square. Again, the total current. We need to find out the total current of the parallel resonance. At resonance, current IL and IC, we know both are equal, and the cancelling giving a net reactive current equal to 0. Then at resonance, the above equations become IT equal to root of I square R plus 0 square, that is equal to IR. The parallel circuit current at resonance. So we know the inductive, the maximum resistance in a previous 2-3 slide before, we told that if the resistance value is more, the current will be less. You can see here, if in this parallel we have a maximum current, maximum resistance, so that we have get the very minimum amount of the current here. So bandwidth and selectivity of the parallel resonance circuit. So bandwidth, that is equal to frequency, resonance frequency divided by Q. So bandwidth, that is the difference between lower cutoff frequency minus, sorry, upper cutoff frequency minus lower cutoff frequency. So quality factor Q equal to R divided by 2 pi FL. So in a previous we can say XL divided by R. So here R divided by 2 pi FL. So 2 pi FCR, that is equal to R into root of C by L for an parallel resonance circuit. So bandwidth of the parallel resonance circuit, we know, is the bandwidth. So if the bandwidth value is increasing, if you are narrowing the quality factor, the maximum current will be increasing and bandwidth will be reducing. So he can see here. So if the value is increasing, we have different values. So if the R value is very low, if the R value is high, if we are increasing the R value, the current will be reducing. If we are reducing the R value, the current will be getting maximum at the resonance frequency. Okay. So I think in this lecture till now we are discussing about the problems in series RLC circuit, and we discussed about what is the parallel resonance circuit and what is quality factor, bandwidth, resonance, and all. Right. So thank you for your listening. So next we can in our second lecture we can solve the problems in this parallel resonance circuit. Until then, take care. Bye.